Hello, students. In this video, we're going to be going over Chapter 10-3, Solving Quadratic Equations. So, what does it mean to solve a quadratic equation? That's what we're going to find out. All right, so this video is going to be instruction only. I will share another video of me doing the quick checks, and then I'm going to share a third video that you're going to use to self-check your work for the end of section exercises. All right, I'm going to need you guys to self-check them before you turn them in. Definitely a good idea to do them first yourself, of course, before you watch me do them. If you want to do it one at a time, I mean, that's true. That's cool too. Okay, so here we go. Normally we skip over the skill check section. Considering the environment we're in, it's not a bad idea to go ahead and do this. I'm going to do this in my video. So skills you'll need to be able to simplify these square roots. All right. I need you to attention to the signs in front of the square root, and I will talk more about them when I do the video. Also, we're looking at new vocabulary. So this has been introduced before, but we're going to see it again in this section. Quadratic equation, the form of quadratic equation, roots of the equation, zeros of the function. You might be saying, hey, wait a minute, Mr. Montoya, what's the difference between a quadratic equation and a function? And see that here in this next activity. This is a look on page 265. It is not going to be something that I expect you to do. I'm just going to use it for instruction. All right, we're going to be connecting what we know about intercepts of a linear equation and intercepts of a quadratic equation. And you may say, well, wait a quadratic formula, excuse me, function. Got to use the right vocabulary. So a linear function. We focus a lot on the y-intercept, right? Especially when we are in standard form for a quadratic function and slope-intercept form for a linear function, because that y-intercept is just sitting there nice and easy for us, waiting for us to graph, because when x is 0, y is -3. And here, when x is 0, y is -4. We get a y-intercept. Well, the solutions to a quadratic function, a quadratic equation, are found here on the x-axis, or um, the roots of the function are here on the x-axis. And when we were looking at linear equations in standard form, let's say 2x minus 3y equals 7, we would substitute in 0 for y and then solve the remaining x value to figure out what that x-intercept is. Well, guess what? We do the same thing here. And what you'll notice is like, well, wait a minute, if I substitute 0 for y, how do I isolate x? I've got an x squared and a 3x. I want you to think about that, and I want you to think about the form of this equation with a b value of 3. In fact, every equation you want to work with in this section is going to have a b value of 0. And you know what we're learning next, hopefully. So anyway, we're going to be talking about x-intercepts. So at first, we're just going to be looking at the graph. All right, does this x-intercept satisfy the function when we use y? Absolutely, it does. 1.5, 1.5, 3 minus 3 is 0. So when y is 0, x is 1.5. Same thing here for this function. If y equals -4 squared is 16, plus a -12, that gives you a positive 4, gives you y equals 0. Here we have an x-intercept 1. 1 squared is 4. 4 minus 4 is also 0. So both of those on the graph represent the value of x when y is 0. This activity. Okay, is that we identify that the x-intercepts when y equals 0, because that is the difference between a quadratic equation and a quadratic function. Quadratic function, we leave y as a variable, or f of x, a function of x. We leave that as a variable, and that represents all possible points that satisfy the function. When we talk about the quadratic equation or a quadratic equation, we're talking about specific specifically when y is 0. So we're talking about this particular value for y only when we're talking about quadratic equation. Now, if I slip up a couple times, um, good job getting it one because I probably will. All right. Okay. Definition. I'm going to let you guys go ahead and read the definition, add that to your vocabulary slide. That is an assignment in Google Classroom. And let's take a look at example one. Example one is going to focus exclusively on finding the solutions to the quadratic equation by graphing. So you graph the entire function, look for where the function crosses the x-axis, and those are your solutions. You are going to have three possible outcomes, either two solutions here, where your vertex is lower than the x-axis and your graph opens up. That means your function is going to cross the x-axis twice. Or here, when the vertex is actually on the x-axis, you will only have one solution. Or when the vertex is above the x-axis and the function opens upwards, it's never going to cross the x-axis, therefore you have no solution. You could also have a negative vertex and have the function open down and also have a no solution outcome. All right, so you're looking for two things, two solutions, one solution, or no solution. And remember that, and I'm surprised they don't put that in this form here, that it is x that equals positive or negative 2. And in this case, it's going to be x equaling 0. I guess because that would technically mean that it represents the whole line. So, I have to rethink how I wrote my answers in the work that I'm going to share with you. So here the solutions are negative 2 and 2. Solution is 0, and then here there is no solution. So of course you have a quick check. You'll be expected to do all three. Go ahead and graph them. Remember, graph is awesome. If you don't, please get a ruler and sketch out appropriate. Make a good looking graph for these. If you don't have a ruler, think again, you could do a sheet of paper cut sideways, with the blue lines of rows that can act as a pattern. All right. So be innovative, be resourceful. You'll be in good shape. Example 2, using square roots. So we can actually, because um, of a unique situation, can simply substitute in 0 for y or for x in the scenario, and then use our properties of equality and solve for x. For example, we have the quadratic equation 2x squared minus 98 equals 0. Let the roots, add 98 to both sides, divide both sides by 2, take the square root of both sides. Remember that we do have positive and negative for the square root of 49. Therefore, our two roots are equals 7 and x equals negative 7. If we were to graph this, that's where the graph would cross the x-axis. Your job is to do the same thing with those three equations there. Now, I will tell you this. If you start with, what do you do when you end up having to take a square root of a negative number? Realize they're for a purpose and try to figure out what situation that represents, solutions or no solution. Quick check three. We are not doing anything or examining anything new other than applying what we know a real world scenario. In this real world example, the city is a circular duck pond. It's technically not circular because that would mean it's two-dimensional. The fact that the pond tells us that we're going to have a third dimension because it's a pond of water. So for the shape of this thing, it is going to be a cylinder, circular surface on top, circular surface on the bottom, and a whole lot of volume in the middle. So in order to what the equation for a volume cylinder is, you don't have to look far because they go ahead and give it volume of a cylinder equals pi r squared times height. In the story, height might mean depth or length if the cylinder is on its side. But either you're going to have equal dimension between the two surfaces. That's going to be the height. And going to have the two surfaces which are circles. Hold on, let me go ahead and get back to that. So in the they give you certain values. One of the values they give you is the actual volume, so you substitute in for volume. Then they give you height, and you substitute in for height. Imagine that you end up with a scenario where you have a value squared, that's your radius, equaling a number on this side, and you have to take the square root of both sides. Now, what's unique about this is that we have no use for that negative value. Negative radius scenario, because we're talking about a duck pond in real life, is pretty useless. So we are only going to use positive value. We're going to estimate our distance for the radius as well as use an estimate for pi. So that's why you see this approximately equal sign here. So that's the answer. The radius of the pond will be ultimately 39.9 feet. Don't forget your units in a real world scenario. Feet. Okay. Your problem that you're working out is the city planning a circular fountain. Imagine that similar to example. The depth of the fountain or the height of the cylinder is going to be 3 feet, and the volume is going to be 1,800. Find the radius of the fountain. All right. So please show all your steps when you solve the problems, and I give all the checks a shot, and then you'll be doing all the quick checks so you can verify your work. Then, as far as independent work goes, I want for you guys to do all of the problems from 1 to 21. If you have graph paper, again, that's going to be super helpful for problems 1 through 9. Problems 10 to 18 is simply solving, so you might have 1 or 2 steps. And finally, example 3. Those are 3 real-world scenarios, all very similar to area of a square problems and one problem. So there's going to be a lot of graphing involved. So please, and the one hint that I'm going to, not hint, but prompt I'm going to give you for 1 through 9 is take a moment to try to determine based on these structures what the graph is going to look like before you start graphing. What kind of scale do you need before you start graphing? Because it is going to be fairly pointless a bunch of graphs with a whole lot of blank space in them, right? If you do not need the whole negative section of the y-axis, then don't waste a lot of space graphing it, all right? Try a little prediction. You should be in great shape. So again, good luck and talk.